Every time you open an app on your phone, whether it's a social feed or your bank or even just a transit map, you're looking at this highly polished, perfectly rendered scene.
Oh, absolutely. The front end gives you exactly what you need, all neatly formatted.
Right. But behind that application layer, there's a totally different reality. We're talking about the raw database layer, where data isn't stored for human convenience at all.
Yeah, it's heavily normalized.
Exactly. It's fragmented into dozens of disparate tables just to optimize storage and, prevent anomalies. So today's deep dive takes us right into that friction point between those two worlds.
It's such a fascinating space to explore.
It really is. We're looking at how data is abstracted and reassembled on the fly so that both the machine and the human get exactly what they want.
Yeah, because it's basically an architectural balancing act. We kind of take it as a given that relational databases break data down into its absolute smallest logical component.
Right, they have to.
But you can't just expose an application to a heavily fragmented schema like that without creating, massive headaches for your developers. The application just wants an answer, not a treasure map.
Yeah, that makes total sense. And the tool that bridges that gap is exactly what we are working with today. We've
Yeah.
got notes and lecture slides from a CS50 presentation on databases with SQL viewing.
A really great set of sources.
Definitely.
Yeah.
Okay, let's unpack this. Our goal today for you listening is to demystify what a database view actually is, um, why it's a secret superpower for developers, and how it simplifies and protects the invisible information we interact with every single day.
And to really appreciate the mechanics of a view, we really have to start with the problem of normalization. The
Yeah.
sources give us this standard entity relationship diagram for a library system.
Yeah.
So we have a core book entity in the middle, and it's surrounded by distinct entities like author, publisher, translator, and rating.
Because in a normalized database, you don't actually store the author's name in the books table. Like if Han Kang writes 3 books, you don't literally type Han Kang 3 times.
No, absolutely not. That risks a typo, which, creates a data anomaly.
Exactly. Instead, the books table just has an integer and ID and the title. So ID1 is Boulder, ID74 is the White Book, ID4 is Standing Heavy, and ID78 is Flights.
Right. And then you have an entirely separate authors table that just maps those IDs to names. So ID 23 is Eva Baltazar, ID 31 is Han Kang.
Okay, I'm with you.
But to link them without duplicating data, the system uses a bridge table. In this case, it's called authored, and it contains no human-readable text whatsoever.
Really? None.
None at all. It is strictly a map of integers, so it just says author ID 31 pairs with book ID 74.
Which is structurally perfect for the database engine, right? It's compact, it's indexed, it guarantees referential integrity, but it's fundamentally hostile to a human reader or even a front-end application that just wants to, display a catalog. The app would have to write this complex multi-table join query every single time. It just needs a simple list of books and authors.
And that is exactly where the view comes in.
Okay.
By executing a create view statement, the sources use the syntax create view name as select a database administrator, is basically saving a complex query as a virtual queryable object right within the database schema.
So is a view basically like a music playlist?
Oh, I like that. How so?
Well, the actual MP3 files or audio tracks are stored deep in your computer's folders, right? But the playlist creates a clean virtual list of just the songs you want to hear right now without moving the original files at all.
That is a perfect analogy. Yeah, that holds up really well. Using that create view W syntax, we can combine those 3 separate tables into one simple readable list showing the title right next to the author's name.
So instead of seeing integers, I just see Boulder by Eva Baltasar or Flights by Olga Tokarczuk.
Exactly. It completely hides those clunky numerical IDs from the user.
Wow. Okay, so it stitches things together neatly. But what happens when there's just too much data to look at individually? Like, how do we extract the bottom line?
That's where we get into aggregating and partitioning data.
Okay, lay it on me.
So consider the ratings entity from our library schema. A popular book doesn't just have one rating. It has thousands of individual user scores, ones, twos, threes, fours.
And no application wants to ingest 50 or 1,000 individual rows of integers just to calculate an average on the client side.
Right. You want the database to just hand you the final number. And the sources show how a view can instantly aggregate these.
Oh, nice.
Instead of writing complex functions in your application code, you bake it into a view. So instead of seeing 50 ratings, the view parses them and just spits out the average. Book 1 simply shows a rating of 3.67 or 2.5.
That's so much cleaner. And the slides also pair this with partitioning, right?
They do, yeah.
They list a data set of books with their publication years. So you've got Whale from 2023, Paradise and After the Sun from 2022.
Right, and minor detail on The Perfect Nine from 2021.
Exactly. So if you're generating reports, a view can partition this data, creating separate virtual tables just for 2023 books, or just for 2022 books.
Yes, but the architecture actually handles these temporary subsets a bit differently than standard permanent views. The sources introduce two specific structures here, temporary views and CTEs.
Wait, if a view is a virtual table, are these just views with an expiration date? Why not just make everything a permanent view?
Well, what's fascinating here is that not all data needs a permanent monument, right?
Fair enough.
CTE stands for Common Table Expression, and it uses the White Taoist name AS syntax. It's incredibly ephemeral. It exists only for the duration of a single query.
Oh, wow. So it's like doing long division on a napkin at dinner.
Yeah.
You need a place to hold the intermediate numbers, but once you have the final answer, you leave the napkin on the table. You don't file it away.
That is exactly it. Once the query is done, the CTE vanishes entirely.
And a temporary view.
A temporary view persists a bit longer for the duration of your whole database session. But the point is, they act like scratchpad calculations. They aggregate the math on the fly for a specific task and then vanish, keeping the database totally clutter-free.
That makes a lot of sense. Structural hygiene is important. But if views can show us exactly what we want to see, can they also be used to intentionally hide what we shouldn't see?
Oh, absolutely. We're moving from convenience straight into security now.
Right, because here's where it gets really interesting. The sources use this surprisingly whimsical data set to illustrate security.
Yeah, the Mario dataset.
Yes, we get a table called Rides Tracking Transportation. It contains an ID, an origin, a destination, and the rider. And the riders are all characters from the Mario universe.
Right, so you have Peach traveling from Good Egg Galaxy to Honey Hive Galaxy.
Or Mario going from Castle Courtyard to Cascade Kingdom.
Luigi heading from Metro Kingdom to Mushroom Kingdom.
And my personal favorite, Bowser moving from Seaside Kingdom to Deep Woods. Now, if you're a real-world rideshare app, your company's analysts might need to see popular routes to optimize traffic.
Sure, they need to know that traffic is heavy between the Seaside Kingdom and the Deep Woods.
But for privacy, they definitely shouldn't see that Bowser is the specific customer taking all those trips to the Deep Woods.
Exactly. Behind the Nintendo references, that table represents highly sensitive data. And this touches on a foundational concept of digital privacy, the principle of least privilege.
Meaning you only get access to what you absolutely need to do your job.
Precisely. If you grant an analyst access to that raw rides table, you've breached user privacy. They can see the routes, but they can also see the names.
So how does the view fix that?
To secure this data, a view is created that only shows the origin and destination. It completely drops the rider column from the virtual table. So from the analyst's perspective, the rider column doesn't even exist.
Wow. The data exists, but the view ensures different employees only have the exact level of access they need.
Exactly. It acts as an API layer, a stable contract between the raw schema and the user.
That is so smart. But it also introduces this massive logical puzzle that the sources spend a lot of time on.
The updatability problem.
Right. We know views are just virtual windows into the real data. So what happens if you try to delete something while looking through the window? You can't delete a reflection.
You really can't. If a view is a complex mix of tables and you hit delete, the SQL engine can't possibly guess your intention. It usually just throws an error.
But the sources show a way around this, right?
They do. They introduce the mechanism of soft deletions managed by database triggers.
Okay, let's walk through their example. The sources show an old postcard of the Museum of Fine Arts, Boston.
Right, the collections table.
Yeah, it's a table of artworks with titles like Farmers Working, Imaginative Land, Profusion of, and Peonies and Tuster.
Yeah.
But there's a crucial extra column here.
A deleted column.
Right, a deleted column filled with edvies.
It's a Boolean column acting as a state flag.
And a view called Current Collections is set up to only show items where deleted equals 0. So what happens when an item, like Farmers Working, needs to be removed by the museum staff?
Well, when an item is removed, SQL uses a trigger. The syntax is literally create trigger name instead of delete on view for each row begin, and then the code end.
Wait, instead of deletes, it's the ultimate undo button.
Basically, yeah.
Instead of actually shredding the file, the trigger intercepts your delete command, taps the database on the shoulder and just quietly changes the 0 to a 1 in that deleted column.
That's exactly what happens. It executes an update statement instead of a delete statement.
And because the view only shows items were deleted as 0, the painting just turns invisible in the view.
Right. By using instead of delete or instead of insert triggers, databases protect against catastrophic data loss. The data is never truly gone. The view just stops showing it.
That is brilliant. It maintains all the historical records without cluttering up the active system.
And if someone makes a mistake, you just flip the 1 back to a 0 and it instantly reappears.
So what does this all mean? We started out looking at how rigid databases are, but it turns out SQL views aren't just technical quirks. They are the lenses that simplify, aggregate, secure, and protect the massive oceans of data that run our world.
They really are the directors behind the scenes of our digital lives, which actually leaves you with kind of a wild thought to ponder.
Ooh,
Consider the apps you use every single day, your bank, your social media, your streaming services. You are never seeing the raw reality of the data. You are only ever seeing a highly curated, deeply secured view.
that's true.
It makes you wonder what exactly is hidden in the columns you aren't allowed to see, and how much of your own erased digital life is currently sitting under a soft deletion, just waiting for a query to bring it all back.
Wow. Now that is something to think about next time you hit the delete button.